Hello, everyone. My name is Juan Gomez-Luna, and I'm a senior researcher in the Safari Research Group at ETH Zurich. Today, I'm going to present our work, benchmarking memory-centric computing systems, analysis of real processing in memory hardware. Let's start with an executive summary. Data movement between memory and storage and the compute units is a major contributor to the execution time and the energy consumption. Processing in memory is a way of alleviating this data movement bottleneck. It's being explored for decades, but only now UPMEM has designed and fabricated the first publicly available real-world processing in memory architecture. It is composed by DDR4 chips that embed in order multi-threaded cores that are called DRAM processing units or DPUs. Our work is an introduction to the UPMEM programming model and PIM architecture, a micro-benchmark-based characterization of the DPU, a benchmarking and workload suitability study. Our main contributions are comprehensive characterization and analysis of the first commercially available PIM architecture and the processing in memory benchmarks or PRIM benchmarks, 16 workloads that are memory-bound in conventional processor-centric systems and that we characterize with strong and weak scaling experiments, and also compare them to their CPU and GPU counterparts. Takeaways of our work are the workload characteristics for PIM suitability, programming recommendations, suggestions and hints for hardware and architecture designers of future PIM systems, and PRIM, the benchmarks that can serve as programming samples and for evaluation and comparison of current and future PIM systems. Data movement in current computing systems dominates performance and energy consumption. These are some numbers that illustrate the energy consumption. And what happens is that among all the components that exist in a compute system, and in between these components and the main memory, there is a lot of data movement. And we believe that a way of alleviating this is turning compute systems into something more data-centric. And processing in memory is a way of doing so, by computing where it makes sense, where the data resides. As I mentioned earlier, the UPMEM PIM architecture is the first real-world PIM architecture that is publicly available. It's composed of DDR4 DIMMs, each of them with 8 or 16 PIN chips, and inside each PIN chip we have memory arrays and we have small cores that are called DRAM processing units or DPUs. We have extensively analyzed this architecture in our work, and we explain that way in our papers. This is a short version of the paper, and this is a longer version. Throughout this presentation and also in our papers, you will find some colored boxes with programming recommendations, key observations, and key takeaways. Let's start with a description of the UPMEM-based PIM system. The UPMEM-based PIM system follows the accelerator model, where UPMEM DIMMs coexist with conventional DIMMs that behave as the main memory. The integration of the UPMEM DIMMs follows the accelerator model, and this means that the UPMEM DIMMs can be seen as a loosely coupled accelerator. So it's necessary to explicitly move data between the main processor and the accelerator, and it's necessary to explicitly launch the kernels, the functions that are going to run on the UPMEM processors. This somehow resembles GPU computing with discrete GPUs. This is the system organization of the UPMEM-based PIM system. As you can see, there are regular DDR4 or regular DDR DIMMs that represent the main memory, and there are UPMEM DIMMs that represent the PIM-enabled memory. If we take a closer look, we see that in each of the UPMEM DIMMs, there are 8 or 16 chips. That is 1 or 2 ranks of 8 chips each. And inside each PIN chip, there are 8 64 banks per chip. These banks are DRAM banks called main RAM or MRAM, and there are 8 DRAM processing units or DPUs. So in total, there are 64 DPUs per rank. In our study, we have used an UPMEM-based PIM system with more than 2,500 DPUs and up to 160 gigabytes of PIM-enabled memory. We have also experimented with a 640 DPU system that contains up to 40 gigabytes of DRAM memory or PIM-enabled DRAM memory. So let's start with basics of UPMEM PIM programming. This is our first programming example, is vector addition. In vector addition, as you know, we just need to perform the element-wise addition of the elements of 2 input arrays A and B, and the results are stored in an array C. So the way that we distribute the computation in an UPMEM-based PIM system is by partitioning the input and the output arrays across the DPUs. So this chunk here will be assigned to DPU 0, this one to DPU 1, DPU 2, and DPU 3, and then inside each DPU, we distribute the computation across the available tasklets that are software threads that run on a DPU. So this would be for DPU 0. This is for the rest of the DPUs. The way to communicate from the host CPU to the DPUs is by doing it through the memory channel. And there are CPU to DPU transfers when we move data from the CPU host main memory to the PIM-enabled memory, and there are DPU to CPU transfers. The UPMEM SDK provides serial CPU DPU transfers where only a single DPU and a single MRAM bank is target. It has also parallel CPU and DPU and DPU CPU transfers where we target multiple DPUs, that is multiple MRAM banks. And finally, there are broadcast CPU DPU transfers where multiple DPUs are targeted, but we transfer the same buffer to all the DPUs. DPU to CPU and CPU to DPU transfers are important because they are necessary for inter-DPU communication because of the fact that there is no direct communication channel between DPUs. So all communication between DPUs needs to happen through the host CPU. And we have experimented with different example communication patterns. For example, merging of partial results to obtain the final result. That's something that only needs DPU to CPU transfers, or redistribution of intermediate results for further computation. In that case, we use DPU CPU transfers and then CPU DPU transfers. We have studied how fast are these data transfers, and I refer you to our papers or to the backup slides in this presentation to see how these data transfer look and what's the sustained bandwidth that can be achieved. Now let's take a closer look at the DRAM processing unit or DPU. So the DRAM processing unit is inside the PIM chip, and in each PIM chip we have a control and status interface and a DDR4 interface. This DDR4 interface is for the host to access the MRAM banks. There are 8 MRAM banks in a PIM chip, and the way of accessing from the DPUs to these MRAM banks is through one DMA engine. The DPU is composed by 2 SRAM-based memories, 1 instruction memory, and 1 scratchpad that is used for operands and intermediate results that is called working RAM or WRAM. And also the DPU is composed by a pipeline of 14 stages. Let's take a closer look at the pipeline. In the DPUs that we have used in our study, this pipeline can run at a frequency of up to 350 megahertz, even though it's a little bit faster in more recent DPUs. The DPU is a fine-grained multi-thread core that can support up to 24 hardware threads, and it's composed by 14 pipeline stages for thread selection, instruction fetch, register file access, operand formatting, arithmetic and logic operations, and access to the WRAM, and finally result formatting. We have extensively analyzed the arithmetic throughput of the DPUs by doing some micro benchmarking. In our experiments, we have used a single DPU and we have changed the number of tasklets from 1 to 24 for different data types and different operations. Here are the results. These are the addition and subtraction results for in 32 for 32-bit integers. These are for multiplication and division, and these are for the rest of data types. One common observation, which is our first key observation, is that the arithmetic throughput of a DRAM processing unit saturates at 11 or more tasklets. Another observation is that DPUs provide native support for 32 and 64-bit integer addition and subtraction, which leads to high throughput of these operations, but they do not natively support multiplication and division and floating point operations. These operations are emulated by the runtime library, and thus the resulting throughput is much lower. In our work, we have also analyzed the bandwidth from the pipeline to the WRAM, but you can find these results in our paper or in other previous talks. Now we are going to discuss about the MRAM latency and the MRAM bandwidth. Our goal is to measure what's the MRAM bandwidth for different access patterns. So we have used different micro benchmarks. First of all, a micro benchmark to measure the latency of a single DMA transfer for different transfer sizes. And then we measure the bandwidth using the stream benchmark. But also we have micro benchmark for strided and random access patterns. So let's start with the latency of a single DMA transfer. These are the results for latency and bandwidth. And one thing that we observe is that we can model the MRAM latency with a linear expression, something like this. In this expression, beta equals 0.5 cycles per byte. So key observation is that the DPU MRAM bank access latency increases linearly with the transfer size, and the maximum theoretical MRAM bandwidth is 2 bytes per cycle. Now let's take a quick look at the stream benchmark results. These are the results for the different versions of stream benchmarks, including the saturation points, performance saturation points of these benchmarks. Key observation is that when the access latency to an MRAM bank for a streaming benchmark, for example, copy or add, is larger than the pipeline latency, the execution latency of arithmetic operations and WRAM accesses, the performance of the DPU saturates at a number of tasklets is smaller than 11. This is a memory-bound workload in the UPMEM PIM architecture. But when the pipeline latency for a streaming benchmark, for example, a scale and triad, is larger than the MRAM access latency, the performance of the DPU saturates at 11 tasklets. This is a compute-bound workload. For the experimental results for strided and random accesses, I refer you to our paper. Now let's take a look at the comparison of arithmetic throughput versus operational intensity. In this experiment, we try to characterize memory-bound regions and compute-bound regions for different data types and operations. So what we do is loading one chunk of data from the MRAM array to the WRAM, and then we perform a variable number of operations on the data, and finally we write back to MRAM. This experiment is inspired by the roofline model. So here are some results. In the memory-bound region, what we observe is that the throughput increases with the operational intensity, while in the compute-bound region, the arithmetic throughput is flat at its maximum. So the throughput saturation point is the operational intensity where the transition between these two regions happen, and we observe that is very low. For example, for 32 integer addition, it is as low as 1/4 operation per byte. And we observe these results for other data types and operations as well. The arithmetic throughput of a DPU saturates at low or very low operational intensity. Thus, the DPU is fundamentally a compute-bound processor. We expect that most real-world workloads can be compute-bound in the UPMEM PIM architecture. Now let's talk about PRIM benchmarks. The idea of developing PRIM benchmarks is to create a common set of workloads that can be used to evaluate the UPMEM PIM architecture, compare software improvements and compilers, and compare future architectures and hardware. We have two selection criteria. First of all, we select workloads from different application domains, and we select workloads that are memory-bound on processor-centric architectures. In total, there are 14 different workloads and 16 different benchmarks. The application domains are dense linear algebra, sparse linear algebra, databases, graph processing, neural networks, bioinformatics, etc. And if we take a look at the 14 workloads on an Intel CPU, we observe that all of them fall in the memory-bound area of the roofline. So they are memory-bound in processor-centric systems and in principle, good candidates for processing in memory. PRIM benchmarks are also diverse in terms of memory access patterns, operations and data types, and communication and synchronization needs. Let's take a look at the evaluation. In our evaluation methodology, we use two different UPMEM-based PIM systems, and we perform strong and weak scaling experiments on the larger system for 1 DPU, 1 rank, and up to 32 ranks. We also perform a comparison to the CPU and GPU counterparts on an Intel Xeon CPU and an NVIDIA Titan V GPU. These are the results for strong scaling experiments on 1 DPU. We change the number of tasklets from 1 to 16, and we show the breakdown of the execution time for the DPU, that is the execution time on the DPU, the inter-DPU communication, CPU to DPU communication, DPU to CPU communication, and the speed up over 1 tasklet. If we take a closer look at the results, we observe that for most of these workloads, the best performing number of tasklets is 16, and this makes sense. It's connected to the fact that the performance saturates at 11 tasklets. And we also observe that most or several of these workloads do not use synchronization primitives. Some of them use synchronization primitives, but the overhead is very lightweight. And while others like BFS, histogram, and transposition use mutexes, which cause contention when accessing shared data structures. If we take a closer look, in this case, at the histogram, we observe that the best performing number of tasklets is not 16 in this case. And the reason is that the intensive use of intra-DPU synchronization across tasklets, in this case, mutexes, may limit scalability. In our paper, we also have results for 1 rank, 32 ranks. These are strong scaling experiments and also weak scaling experiments. With respect to the comparison to CPU and GPU, as I said, we compare to a Xeon CPU and a Titan 5 GPU. And here are the performance comparison results. These are the more PIM-suitable workloads. These are less PIM-suitable workloads because they don't perform so well. And here you see the GeoMean results. Observations are that the larger, well, both systems actually outperform the CPU for all benchmarks except SPMB, BFS, and Needleman-Wunsch. And both systems are respectively 23 times and 27.9 times faster than the CPU for 13 of the PRIM benchmarks. In comparison to the GPU, the larger PIM system outperforms the GPU for 10 PRIM benchmarks with an average of 2.54 times, and the performance of the smaller PIM system is within 65% the performance of the GPU for these workloads. Key observation here is that the UPMEM-based PIM system can outperform state-of-the-art GPU on workloads with 3 characteristics. First, streaming memory accesses. Second, no or little inter-DPU synchronization. Third, no or little use of integral multiplication, integral division, or floating point operations. These 3 characteristics make a workload potentially suitable for the UPMEM PIM architecture. In terms of energy, we observe that the smaller PIM system consumes on average 1.64 times less energy than the CPU for all 16 PRIM benchmarks. Finally, some key takeaways. First of all, the UPMEM PIM architecture is fundamentally compute-bound. As a result, the most suitable workloads are memory-bound on conventional processor-centric systems. Second, the most well-suited workloads for the PIM architecture use no arithmetic operations or use only simple operations like bitwise operations and integral addition and subtraction. Third, the most well-suited workloads for the UPMEM PIM architecture require little or no communication across DPUs. And finally, the UPMEM-based PIM systems outperform state-of-the-art CPUs in terms of performance and energy efficiency on most PRIM benchmarks. They outperform state-of-the-art GPUs on a majority of PRIM benchmarks, and the outlook is even more positive for future PIM systems. And these UPMEM-based PIM systems can be more energy efficient than state-of-the-art CPUs and GPUs on workloads that they provide performance improvements. To finalize the executive summary, again, data movement is a major contributor to execution time and energy consumption. Processing in memory can alleviate this data movement bottleneck, and UPMEM is the first real-world processing in memory architecture that we have studied in our work, and we contribute a comprehensive characterization and analysis of the first commercially available PIM architecture, and we create the first benchmark suite PRIM for a real-world processing in memory architecture. Key takeaways of our work are the work characteristics, programming recommendations, suggestions and hints for hardware and architecture designers, and the PRIM benchmark suite. This is a short version of the paper. This is the long version of the paper, and if you want to learn more about this architecture, you can watch some of our previous talks, for example, this one. All our codes are available in our repository. And we continue working on understanding the UPMEM PIM architecture. This work, SPARS-P, is about sparse matrix vector multiplication on the UPMEM PIM architecture. Here, we explore different ways of implementing SPMB using different ways of partitioning the work across threads, for example, 1D partitioning and 2D partitioning, different ways of synchronizing coarse grain, fine grain, and lock-free, and in total 25 SPMB kernels for these UPMEM-based PIM systems that you can see in this slide. This is the sparse paper. You can also access from here the repository, and it's just one of the works that we are carrying out. Another one is a framework for high throughput sequence alignment using real processing in memory systems, or an experimental evaluation of machine learning training. Some of these works were presented in the special session that we organized in the ISV-LSI conference in July. And we also talk about these works and also about other PIM architectures in our processing in memory course. We have also other project and seminar interesting project and seminar courses, such as this one on heterogeneous systems, or others on DRAM, SSDs, genome analysis, etc. That's all for today. Thank you very much for your attention.